They're for profit, but also do good, I guess is the idea. And they do a program called Summer of Maps, where they bring students in a variety of programs, but with data visualization and GIS skills, to Philadelphia for the summer to work with nonprofits, and each student works with 2 nonprofits. And nonprofits apply with projects that students are going to do. And we applied at Constance and I put together an application after. Who turned us on to this? I was trying to remember, was it Ed or was it yes, okay. Roger heard about this opportunity and sent it our way. So we proposed a project, and we were accepted, and Sarah has taken on, and we made our nonprofit name. We chose the Fairtech Collective, my research group, as the nonprofit, with the understanding that there was actually quite a coalition of nonprofits involved in this, or of groups, let's say, whether nonprofits or not, groups. And Sarah has done some wonderful work for us. So she's going to present that today. Sarah, is it okay with you if I record this?
Yes, yeah, that would be great.
Okay. And she'll ask for your questions at the end. She's asked people to hold questions until the end. Okay.
Great. Awesome. Hi, everyone. I'm Sarah, and the project that I worked on this summer is titled Petrochemical Pollution Footprint in the San Francisco Bay Area. First, just a little bit about myself. My name is Sarah Gates. As mentioned, I'm working as a Summer of Maps Fellow at Xavier. I'm currently pursuing my master's in Geographic Information Science for Development and Environment at Clark University, and I got my bachelor's in Environmental Studies at Bryn Mawr College. It was there that I sparked my interest in environmental justice issues, and as I've learned more about GIS and using maps, I've really become passionate about using maps to communicate data, especially complex environmental data. First, just a little overview of this project. I had several project goals coming into this, and the first was to visualize the impact of refinery flaring pollution from the major petrochemical refineries in the San Francisco Bay Area. Next, I wanted to assess the presence of sensitive receptors that are located in close proximity to these refineries, and then investigate the relationship between concentrations monitored by fence line monitors and the flaring activity of refineries. And finally, and what I consider most importantly, I wanted to communicate my results with a series of infographics that would combine maps, graphs, and text to kind of bring all of it together and create a narrative about this issue. So first, to just frame the issue a little, here are the locations of the 5 major refineries within the San Francisco Bay Area. They're spread across several different communities, and the main goal is to kind of look at how these communities may be affected by these refineries and help to kind of understand some of the data that is out there about the refinery pollution and how that relates to public health and the well-being of the environment. So the first data set that I worked with was flaring data. This image shows an example of flaring at the Tesoro refinery in Martinez. And flaring occurs when a petrochemical refinery has to release large quantities of gas, flammable gas, through a flare stack. Oftentimes it could occur in an emergency if there's a power outage and there's kind of a large backup of flammable gas that needs to be released. However, it's up to debate whether refineries are actually flaring more than they need to be. So the data that I worked with was reported by each of the refineries to the Bay Area Air Quality Management District. They report their daily flaring activities, and then this is broken down by each pollutant. So there are more than one flare at each refinery. There's anywhere from 2 at the Phillips 66 refinery to 7 flares at the Chevron refinery in Richmond. And each flare has different kind of combinations of pollution that come out based on like the product, the petrochemical product that flare is kind of releasing from. So the 3 pollutants that were included in this flaring data are methane, non-methane hydrocarbon, and sulfur dioxide. So the original plans I had for this data were to do some type of dispersion modeling. However, I quickly realized that the amount of data that you need to do this type of modeling is immense. It requires like large, really large scale kind of weather data, meteorological measures, and just data that I was not able to access, and also programs to model it that I was not able to with kind of the time constraints and the possibilities to perform an analysis this summer. However, I really still wanted to visualize this data and understand the spread. So I started to think about other ways to do this. Maybe I would create some graphs showing pollution during different months of the year, maybe showing it on a map so that you could see where exactly in relation to the communities this pollution is coming from, and perhaps creating a series of these graphs and maps over time to see change over time. And then I thought, why not combine all of these into one animation to really get a sense of the change over time over this 2-year period. So I created kind of a first very rough wireframe of what I wanted this animation to look like. My idea was to have kind of a map that would symbolize the amount of pollution with a circle that was proportional to the amount of pollution released during a certain month, have a map for each month within the 2015 to 2016 time period, and then have a corresponding graph for each refinery that would show the daily pollution flared. However, when I created kind of a test of this and I animated it, I realized quickly that it became much too complex to show the data in this format. There's just a lot of information flashing by quickly, and it was really difficult to kind of pick out the details that are described by the daily graphs. And I also ran into another huge problem, which is the scale of the graphs. Here you can see, for example, during this month, Chevron only emitted 5 pounds of pollution from flaring, whereas Phillips 66 emitted over 37,000 pounds. So while it looks like the same amounts when you're just looking at the graphs, looking closer at the legends or the axes show that it's actually quite different amounts. So to solve this problem and to make it more easy to kind of animate and flash through quickly, I decided to simplify this and just have one graph along the bottom that would show the pollution for each refinery for the entire month, and would include different categories of sulfur dioxide, methane, and non-methane hydrocarbon to describe each type of pollution. And so this is the result of the animation that I created. It cycles through, and I think what is most powerful about this animation is the map and how it kind of shows the spread of pollution, even though it's not necessarily a accurate representation of where this pollution spread to. It gives you a sense of the quantity of pollution that was emitted each month by flaring, and what communities nearby may have been affected by this flaring activity. Also in the bottom, you can see kind of a more detailed breakout of what pollutants were being emitted during a particular month, and you can compare between the different refineries, which one had more or less during a particular month. So after doing the flaring data analysis, I moved into looking at sensitive receptors. So who is a sensitive receptor? It's a person who is more vulnerable to the negative health effects of pollution, namely people who are very young and very old. I also considered facilities that have high sensitive receptor concentrations. These include places where we live, work, play, and learn. So the facilities that I looked at for this data were schools, daycare facilities, hospitals, and long-term care facilities. At first, I just kind of calculated the number of facilities that fall within 2.5-mile radius of each refinery. As you can see, just glancing at these numbers here, Shell has the highest amount of facilities within 2.5 miles of the refinery. And it's also interesting to note that the two facilities within 2.5 miles of Tesoro, so one school and one daycare, those both fall within the 2.5-mile radius of Shell as well. So there are two facilities in this area that are actually within this buffer distance of more than one refinery. And then I thought, what better way to show this data than to put it on a map and create a visualization of where these sensitive receptors are and show them within a 2.5-mile radius of the refinery. It's also interesting to note, looking at this, it's 2.5 miles from the center of this refinery, and oftentimes these refineries can be up to like a half mile across. So these facilities really may be closer to the fence lines than 2.5-mile radius buffer shows. And this map kind of gives an idea of where these sensitive receptors are clustered, where there are more hospitals and long-term care facilities, and where there are high concentrations of schools and daycare facilities, places where children are. And the next analysis I did was to look at children and elderly populations. So for this, I used census data, and I calculated the number of people who are under the age of 18 or over the age of 65 living within each census block. I divided that by the total population in the block to get a number of the percentage of people living within each census block that are sensitive receptors. Interesting to note that the census block that contains the Phillips 66 refinery, there are over 50% of the population there is considered a sensitive receptor. So after looking at the sensitive receptor data, I wanted to look at the fence line monitoring data. The fence line monitors are set up around two refineries within the area, Chevron and Phillips 66, and there are some that are located actually along the refinery fence line and some that are located further into the communities. And these monitors are important to allow communities to track air toxin concentrations in real time. This picture just shows an example of what a fence line monitor may look like, and this data is really important for determining the levels of hazardous pollutants near these refineries. Here shown with the blue triangles are the locations of the monitors in relation to the two refineries. Important to note that there are only the two refineries that have this many fence line monitors located around them. However, with new regulations, the other refineries are going to be required to add these fence line monitors, thereby allowing the communities of Martinez and Benicia to better monitor these concentrations. So my original plans with the fence line monitoring data were that I wanted to perform an interpolation. This image here just gives an example of what an interpolation analysis could look like. You start with kind of a series of points spread across a space, and then you create an output surface that shows concentrations over an area, showing where clusters of high concentrations of pollutants are and low. So this was originally what I had hoped to be able to do with this data. However, there were not enough points to use. This was a result of just very few fence line monitor locations, only maybe a maximum of 9 near each refinery, and also the issue that the fence line monitors are all different and they monitor different concentrations of pollutions. So for example, some of them had data about sulfur dioxide and some did not, and some monitored benzene, some did not, some only had wind speed and wind direction. So the kind of lack of data points made this analysis impossible. However, I do want to note here that the solution to be able to do an interpolation analysis is to increase the number of monitors. So with additional monitors at other refineries in the areas and increasing the number in the communities of Richmond and Rodeo would allow for this interpolation analysis to be done in the future, which I think would be a really interesting thing to take on moving forward with this project. And I think it could be really interesting for someone to try to conduct an interpolation analysis, and that could really provide some powerful insight into where there are especially high concentrations of pollutants. So I didn't want to just kind of completely ignore this monitoring data. I still think it's very important, and I wanted to see how I could kind of combine this with the analysis that I'd already done. So I decided to investigate the monitoring concentration data in conjunction with some of the flaring data. So here I selected a period of really high flaring activity at the Phillips 66 refinery, and I combined it with two fence line monitors that are located nearby. I wanted to look at if location mattered. So the Rodeo North fence line, which is the blue line on the graph, is located right along the fence line of the refinery, and the Crockett monitor is located further out. And upon kind of first looking at this graph, it does look like, for example, around January 22nd and 23rd, on those high flaring days, you do see corresponding increases in sulfur dioxide concentration measured at these refineries. However, you will note that on the one day of kind of very high flaring activity, you don't see kind of as much of a response, especially from the Rodeo North monitor. So I think it's important to note that flaring does not kind of encompass the only type of pollution that's output by these refineries. There's regular kind of levels of pollution that are maintained. And also monitors could pick up things like pollution from vehicle traffic. So comparing the fence line and flaring data, it's not a perfect correlation. You're not going to see kind of exact matching patterns. However, I think it is really interesting to note that the fence line monitoring concentrations can provide insight into the changes in air quality as a result of flaring. So for example, if you lived in one of these communities and you drove by, saw that the refinery was flaring, you could see the flares from quite some distance, and you were concerned about air quality, you could use this real-time concentration data to determine if air quality was being impacted at that time. So finally, after conducting kind of these different analyses, I wanted to focus on how best to communicate my results. So up until this point, I had created the animated GIF of flaring concentrations or flaring pollution over time. I created the map of sensitive receptor facilities, the map of the sensitive receptor population, and I compared the flaring and fence line data. And then I wanted to bring this all together in an infographic. And this combined several different maps, some text. I added some additional graphs to kind of highlight these. And my goal with this was really to communicate to a broader audience, to simplify this data in a way that could be understood by more people and to really communicate the issue. So I'll run through this, and I also want to note as I'm introducing this that this is kind of a working draft, and I'm really interested to hear any input about any like either text that should be changed or additional things to include, things to change. I'm very open to that feedback and looking forward to it. So I started with just kind of a general description of the petrochemical pollution in this area, highlighting the facility locations. And then I talked a little about the flaring activity and visualized that data from 2015 and 2016 in just a graph that shows the amount of pollution that was flared at each facility in these 2 years. I talked a little about sensitive receptors, including the map of sensitive receptors, and then breaking it down by the number of sensitive receptors within the radius of 2.5 miles of each refinery. I included the sensitive receptor map by age to show the census block groups that have populations that are more susceptible to pollution from these refineries. I talked about the fence line monitoring data too, showing the locations of these monitors, talking about why it's important, and pointing out that there will be more additional monitoring in the future. I also included this graph of the relationship between flaring activity or monitor detected concentrations. Right now, I'm actually working on trying to calculate the maximum hourly averages of pollutants that were captured at the different fence line monitors throughout 2016. So I may swap out this graph with another that shows kind of like the maximum hourly concentrations that were monitored. I think it might be interesting to see kind of the peak concentrations that were observed at the different monitors. And finally, for visualization, I'm going to break out selected events and create maybe a series of 4 infographics, one for each community, that breaks out selected events at the refinery that falls within this community. I included this image here that's from a news article about excessive flaring at the Tesoro refinery in 2015. This is kind of an idea of what I'm thinking to include within this selected events infographic. It'll have like similar design elements as the infographic I already created, but perhaps including a graph of the like highest amount of flaring during a certain month of that refinery, and then pinpointing whether it's news articles, sometimes health alerts are posted during these flaring events. So trying to connect the data and the numbers of, you know, amount of pounds of pollution and trying to relate that to real life, what images of what you may see driving past the refinery, or reports of health reports, anything like that. So I want to thank you for joining me today and listening to this. I'm really looking forward to any questions you have, and looking forward to hearing any feedback that you may have about the infographic or selected events that I created. Thank you. So that one is, I believe, let me bring it back up here. That one shows 2016. Yes, definitely. Mm-hmm. Mm-hmm. On this, or on the map of the flaring, or? Okay, in the infographic, perhaps in this. Yeah. Okay. Yeah. There, I talked about the number of actual like physical flares. So there, for example, the Phillips 66 refinery has like 2 physical flare stacks, and the Chevron facility has 7. Those were the 2, like, yeah, yeah, that's stacks. Perhaps I'll add some text there that describes that they're stacks. Great. Okay, great. Definitely. Thank you.
I think it would be important to also indicate what is not caught by the fence line monitors. As you can see, during the very heavy flaring incident, the fence line monitors only caught a few things. And so there are all sorts of things that come out of those stacks that are not monitored. So it would be good to have that listed.
Yeah, definitely.
Like lead. Apparently Phillips 66 is one of the biggest emitters of lead.
Oh, interesting.
Yeah, hi Nancy, it's Denny here. That's a very good point. I think we need to note that I believe the data you're relying on, and this is really a great presentation. Thank you very much for pulling this together.
Yeah.
Thank you.
Is that it's relying on the Air District data.
Mm-hmm.
So we fought very hard for 20 years to get flare stocks monitored at all for methane, non-methane hydrocarbons, which is benzene, a bunch of the bad stuff, and sulfur dioxide. But still, that monitoring is very limited, at the actual source. And that was the purpose of the fence line monitors, was to try to track at the fence line, and then in the Richmond situation, see what might fall down in the community. I did have a comment on the sensitive receptor page, if you can bring that up for the refineries and Chevron. Because I know, and I've done these studies before. Yeah, no, that's good. Yeah, right there. No, yeah. I've had to do this before where we map, schools and hospitals and stuff near refineries. The problem is that, particularly with the Chevron refinery, by using the location you have there, the center of the refinery,
Yeah.
that's not where the major operating units are. And if you could bring up the community map, the one that shows the actual neighborhoods, yeah, that's the one. So that point that you're measuring from is not, really accurate. It looks like, Chevron gets kind of a pass on sensitive receptors, and that's not the case. You can see the dark area there to the north, that's North Richmond. Actually, that's where most of the major operating units are, within several hundred feet of the neighborhood. So it gives a sort of a distorted picture. In other words, if you were to move that location up to where the major operating units are now, which is something we fought to get those units out of the neighborhood, up, to the north, it would look more like Rodeo and Benicia.
Yeah,
it would. And so I think that that's important to figure out a way. I know there needs to be uniformity within the study is to regard to where the refinery is located. And unfortunately for people in Rodeo and Benicia, you're kind of like right in the middle of it. You don't have the luxury of being away from the center of where you would logistically say the refinery is. But the Chevron refinery is really adjacent to North Richmond. And so there's a way to correct that without, changing, the parameters of the study. I think that would be important because I think it gives gives them too much of a clean bill of health.
Yeah, definitely. Yeah. That's good that you noted that, because that's something for me I did have concern. Well, these refineries are so large, like how do I figure out where this pollution's actually coming from within kind of the whole complex? So it's good to kind of hear your perspectives on it, because I've never kind of been to this area, so I can only, I try to infer as much as I can from looking at like satellites and Google Earth, but it's good to hear kind of perspectives of where this pollution is actually located, because these were just kind of selected as what I saw to be like the best center.
Sure, and sure, I understand that it's such a huge facility. So down like where you have your dot now, that's where the administrative buildings are, and where they ship out lubricants and things like that. There's not a lot of, they're not manufacturing gasoline down there. They're doing that up by North Richmond and the other petrochemical products they manufacture. So that gives, sort of a, it's so much bigger than the other facilities, but it's hard to hone in on that. So I recognize that. Thanks for that.
Great, thank you. Yes.
Yeah, I wonder, that's another point I had, and thanks for bringing it up, Constance, is whether we should, I think, show the wind direction, because it is prevailing from the west and the southwest, and what happens with that is that all this stuff gets kind of mixed together and it's blown in a certain direction. It's not just going straight up in the air. We know that.
Mm-hmm. Sarah, this is Dawn. Could you go over to the graph where you had the flaring data and the combined with the monitor data?
Yes.
Which I just thought was really, really interesting. Yep, that one. The discussion of wind made me think about this one. I just want to also state my appreciation for how much work has gone into this. It's really, really great work. Now, when I look at this, this really sheds new light for me anyway on what's happening with the monitor data, in the sense that you've got, we know something happened on this date, and yet isn't it interesting that the monitors are showing something slightly different, and sometimes it's time delayed, which is kind of, I'm not sure what to do with that yet, but it does teach me to be both cautious about, okay, when I'm looking at the monitor data, it might not be reflecting reality, so I have to look at the other monitor as well. Yeah, there's just something really interesting going on in this graph, and I just really appreciate you putting it together.
Yeah, I have a suggestion there, a theory. Flares happen at the top of tall stacks. Okay, so the chemicals released by them are dispersing from way up high. It seems to me entirely plausible that the reason you don't see a signature for the biggest flare on the closest monitor is that it just shot right over that monitor at first, but you see it shows up on the other one, right? It shows up on the further away monitor sooner.
Yeah, that's right.
And then you see, what's interesting to me is that you see the more local consequences of it later. And what Ed suggests from the flaring incident in Benicia in May is that the aware didn't pick up anything right away. So he was close to it, didn't pick up anything right away, but then later there was something. So don't know, but these are possible ways of looking at it. And I think, Sarah, I wouldn't be too quick to attribute those things to other pollution sources. I think it could have to do with the nature of the flaring and the dispersion from flares.
Yeah, no, I think you're right, Gwen. And the other thing to point out is that none of these systems, Rodeo, Richmond, Benicia, were designed actually to track monitoring air pollution from flares. That's not part of the design. They're designed to track the ambient concentrations of toxics that are crossing the fence line from sources other than flares. So the fact that we can, look at the data and try to, extrapolate what might be coming from the flare is helpful. And the other thing to know that during a flaring incident, the flare is not the only thing that is letting loose. When you have a major upset at a refinery, the flare is the last resort to chuck the gas out somewhere and burn it before the plant blows up. And that doesn't mean, like in the case of the Chevron accident back in August 5 years ago, that there aren't huge areas of the refinery leaking out toxics as well that are not making it to the flare. So we have to understand these flaring incidents in the context of what's happening at the refinery. And it's not, the flare is the very visible and very scary, manifestation of what's happening at the refinery, but it has no bearing on the totality of what's being emitted from the plant.
I thought it was really great. And it seems to me that that map of the sensitive receptors should be submitted for a comment, if we can do that, to the current Phillips 66 debate, because it really shows how many people, that's a really sensitive area, and they really should not be doing anything that's going to increase the pollution in that area.
I'm curious to know how many people are actually living in that one census block group. Sarah, the really dark colored one there that you pulled out in the infographic.
Yes, I glanced at that today when I was just pulling out a statistic for the infographic, and it was around, I want to say 11 or 1,200 people.
Oh, okay, so significant.
Yeah.
I'm sorry, that's 1,200 people in that black area alone. Is that right?
Yep.
Thank you. I was able to take a screenshot of that as it was hanging up there, so that's great. I'm going to include that in my comments to back my.
We can. The intent here is that that 3-page infographic plus all of these maps and things those are Sarah's deliverables, and she'll be handing them to us to do whatever with, including that kind of work to put in the Phillips 66 comments. And I don't know, Constance, I imagine you'd want to make this part of your presentation on the 5th. Yep. Oh, yeah, good point. Yes. And we can also have these printed to do handouts at the farmers market and things like that too.
That'd be great.
What do you think, Sarah?
Yeah, I think that's definitely doable. The infographic as it stands, I really only have a few tweaks to make based on feedback, but that should be ready to go. And the presentation also will be shared with you for any future use.